Next, we'll take a look at comparators, which is a Java mechanism that helps us sort the same data on different sort keys in different orders. And you're familiar with this. Your music library, maybe at one point you sort it by the artist's name. In this case, we're looking at the Bees. But in another situation, you might want to sort it by song names to look through it by song names. That's the same data using different sort keys. How do we arrange to do something as natural as this in our Java sorts? Now, we used before, in order to be able to implement sorts that can sort any type of data, we use Java's comparable interface. And the concept is that there's some natural ordering of the data that you'll want to use most of the time. That's what the comparable interface is all about. But there's a different interface called the comparator interface, which is a way to help us sort using some alternate order or many different orders on the same data. And the comparator interface, again, just says that it's going to implement a method compare that compares two different keys of a given type, of the generic type. Again, it has to be a total order. And this is very familiar. For example, with strings, there's many different ways that we might want to sort strings. We might want to use the natural alphabetic order, or we might want to make it case insensitive, or maybe there's different languages that have different rules of the ordering. We're sorting strings, but we're implementing a different ordering, various different orderings on that same data. That's what the comparator interface is for. So the Java system sort will have a different method to implement comparators. And the idea is that you create a comparator object and then pass that as a second argument to Java's sort routine. And we can do the same thing for our sorts. The idea is we want to decouple the definition of the data type from the definition of what it means to compare two items of that type. With the natural order, we had to put the definition of compare to within the data type. With comparators, we can do that outside of the data type, even at some later time. Strings were defined as part of the Java system, but we can define our own ordering on strings with a comparator. So in our sort implementations, we can change them as shown in this example to support comparators. To support comparators in our sort implementations, we'll pass an array of objects instead of array of comparable, and then as a second argument, pass a comparator. Then the less method will take that comparator as an argument, and it's the one that actually invokes the method compare of two different keys. This is a straightforward modification to our sorts. And then exchange, of course, rather than doing comparable, has to use object. So with these straightforward changes, add the comparator as argument to the sort and to less, and make our array to be sorted array of objects. It's easy to convert any of our implementations to support comparators. To implement a comparator, you can use this code as a model. I won't go through it all in detail, just to point out that this implements two different comparators as nested classes. So, say for this fictional class student that's got two instance variables, name and section. And the first one, called by name, implements a comparator for students. And when you compare two students by name, it's going to use the string compare to method. If you're going to implement it, compare two students by section, then it'll return just the difference of the sections, which is minus if less, 0 if equal, and plus if greater. And this code is a straightforward way to implement comparators that you can use as a model if you need to be able to sort data on two different keys. So here's just an example of what happens if with those implemented comparators for that class student using the Java system sort. If you call arrays.sort with your array of students and you give it this by name comparator, it'll put them in order, alphabetical order by the name field. And if you give it the by section comparator, it'll put them in order by the second field. Very convenient for all kinds of data processing applications. And we came up with that before when we were talking about using a sort for the gram scan. We needed to have a comparison for points that orders them by the polar angle they make with a given point P. That's what we needed for the gram scan algorithm for the convex hull. Points are a defined data type for geometric objects, and so what we need is code that'll compute the polar angle and use that as the basis for comparison. There's an easy way to do this based on CCW that is described here in this text. Most of the time, all you need to do is do the CCW of the 2 points, but you do have to check whether one of the points is above P and the other one is below. But otherwise, usually it's a CCW call. And this code, which again I won't go through in detail, is an implementation of a comparator for 2D points. It implements the compare method that takes 2 points as argument, and with just a little bit of calculation, it's able to do the compare. So this code is the basis for applying the system sort method, or any sort method, for the gram scan for the complex hull that we did at the end of the last lecture. So that's the basis for the gram scan method for the complex hull that we used at the end of the last lecture. Welcome back. Today we're going to look at merge sort, which is one of 2 classic sorting algorithms that are critical components in the world's computational infrastructure. We have a full scientific understanding of the properties of these algorithms, and they've been developed as practical system sorts and application sorts that have been heavily used over the past 50 years. In fact, Quicksort, which we'll consider next time, was honored as one of the top 10 algorithms of the 20th century in science and engineering. In this lecture, we're going to look at merge sort, which is the basic sort in plenty of different programming systems, including Java. Next time, we'll look at quicksort, which is also used in Java for different applications. All right, so basic merge sort algorithm, what's it going to look like? The idea is very simple. What we're going to do is divide an array into 2 halves, recursively sort each of the halves, and then merge the result. That's the overview of merge sort. It was actually one of the first non-trivial algorithms implemented on a computer. John von Neumann realized in the development of his EDVAC computer, one of the first general purpose computers, that he was going to need a sorting method, and he came up with merge sort. He's widely credited as being the inventor of merge sort. So the idea of merge sort is based on the idea of merging. And so to understand how merging works, we'll think about the idea of an abstract in-place merge. So we've got an array A, and its first half is sorted, and its second half is sorted. And the computation we need to perform is to replace that with the sorted array where those 2 subhalves are merged together. Let's look at a demo. The method that we're going to use is based on taking an auxiliary array to hold the data. This is one of the easiest ways to implement the merge. So the first thing we do is copy everything over to the auxiliary array. Now, once that's done, what we'll want to do is copy back to the original array, but get it in sorted order. In order to do that, we're going to maintain 3 indices. I, the current entry on the left half, J, the current entry on the right half, and K, the current entry in the sorted result. So the first thing we do is take the smaller of the 2 entries pointed to by I and J and compare those, and take the smallest one and move that one to be the next item output. And whichever one is taken, we increment its pointer. Now we compare the minimum again. Again, the one pointed to by j is smaller, so we move that one to k, increment that pointer j, and also increment k. Now there's two e's equal. We always take the first, so the one in the left array goes to k's position, and now we increment I in k. And again, it's an e, and they're equal, but we'll take the first one, so we move that one up, increment I in k. Now jz is smaller than g. It's the next thing that has to go in the output, so we move that one up and increment j and k. Now the one pointed to by i's, the g is smallest, so move that up, increment I and k. Move the m up, increment I and k. Now the last element in the left subarray is the one that's going to get moved next. And now that first subarray is exhausted, so really all we need to do is take the rest of the elements from the right part and move them back in. Actually, since we copied, we could optimize by avoiding these moves. That's an abstract in-place merge. For taking the two sorted subhalves of an array, use an auxiliary array, move them out, and then put them back in sorted order. All right, so here's the code for merging, which is quite straightforward from the demo. We first, in order to sort an array of comparables, in this implementation, we pass a link to the auxiliary array in as well. And we have three arguments, low, mid, and high. So low is the first part of the array to be sorted. Mid's the midpoint that divides the first part from the second. So our conditions are that from low to mid is sorted, and from mid plus 1 to high is sorted. So the merge implementation, then the first thing it does is copy everything over to the auxiliary array. And then that sets up for this for loop that accomplishes the merge. We start our I pointer at the left part of the left half, the J pointer at the left part of the right half, that's mid plus 1, and we start the K pointer at the beginning low. And for every value of K, what we're most often doing is comparing whether aux of J is less than aux of I. And if it is, we move the element at J over and increment J. If it's greater, we move the element I over and increment I. And then in both cases, we increment A, and that increment K, and that implements the merge. If the I pointer is exhausted, then we just move over the J, next Jth element. If the J pointer is exhausted, we move over the next Ith element. So every time we're moving a new element into K, and that's the code that implements the abstract in-place merge. Now, with this code, we're also introducing the idea of making assertions just to make it easier to debug in our code and to have confidence that it's correct. In this case, this insertion just says we want to be sure that A of low to mid is sorted and that mid plus 1 to high is sorted before our code, and then we want to check that the whole thing is sorted after our code. And generally, Java programmers know that it's a good idea to try to do these assertions. Not only does it help detect bugs, but it also documents what the code is supposed to do, and that merge code is a good example of this. If you put at the beginning of the code what you expect in the form of an assertion, which is code itself, and you put at the end of the code what you think it's going to do, again in the form of an assertion, you're both testing that these conditions hold and also telling someone reading the code what you're trying to do with it. So Java is just an assert statement, and it takes a Boolean condition. In this case, we're using that method is sorted that we wrote before that returns true if the part of the array is sorted and false if it's not. And what assert will do is it'll throw an exception unless that condition is true. Now the thing about assertions in Java is that you can enable or disable them at runtime. And that's really important because it means that you can put them into your code to check while developing, but it doesn't incur any extra costs at all in production code. So by default, assertions are disabled. Something goes wrong, somebody analyzing the situation can enable insertions, and they often will help find out what the problem is. So the best practice is to use insertions just as we did in that example with merge, and to assume that they're not going to be there in production code. So you shouldn't use them for things like checking if the input is the way you like it. All right, so with that merge implementation, then the sort implementation is a quite simple recursive procedure shown here. So we use the merge procedure we just showed, and then our sort procedure, it's recursive, so checks that we have something to do first, then it computes the value of the midpoint, same way as we did for binary search, sort the first half, sort the second half, and then merge them together. And then the actual sort takes just the one argument of the array, creates the auxiliary array, and then uses that. Now, it's important to not create the auxiliary array in the recursive routine, because that could lead to extensive cost of extra array creation. And you'll sometimes see merge sort performing poorly because of that bug. Otherwise, this is a very straightforward implementation, and it's actually a prototype for algorithm design that we'll see come up again and again. It's called divide and conquer. Solve a problem by dividing it into two halves, solving the two halves, and then putting the solutions together to get an appropriate answer. Here's a trace of what merge sort does, and if you haven't studied a recursive program before, it's worthwhile studying this thing in some detail. This gives exactly what happens during each of the calls to merge. We start out with a big problem to solve, but we divide it in half, then we divide that one in half, and then we divide that one in half. And the very first thing that we actually do is just compare and exchange, if necessary, the first two elements. And then we do the same thing for the next two elements, then merge those two together to get the first four done. And then we do the same thing for the next four in the array. So now we have two sorted subarrays of size 4. We merge those together to get one of size 8. And then we do the same thing on the right. And eventually we have two 8s that we merge together to get the final result. Very instructive to study this trace to really understand what this recursive algorithm is doing. So now we can animate, and again, merge sort's more efficient, so we can do more and more items. You can see it's got the first half sorted, now it's working on the second half. And then once it gets the second half sorted, then it's going to go ahead and merge them right together to get the sorted result. And it's got a little extra dynamics in the animation because of the auxiliary array. Let's look at it when it's in reverse order. Again, it gets the first half done, now it's working on the second half. Once it gets the second half done, then it goes ahead and merges together the whole thing. It's just as fast on reverse ordered as in arbitrary order. So you can run merge sort on huge problems. It's a very efficient algorithm. And so, for example, what this table shows, if you were to try to use insertion sort for a huge file, say a file of 1 billion elements on your PC, it'd take a few centuries to finish. Even on a supercomputer, if you're using insertion sort, nowadays it'd maybe take a week or more. But if you have a good algorithm like merge sort and you're trying to do 1 billion items, you can do it in just less than half an hour on your PC, and a supercomputer can do it in an instant. And smaller problems only take an instant even on your PC. So you can spend a lot of money or a lot of time, or you can use a good algorithm. And that's one of our main themes in this course. A good algorithm is much more effective than spending money or time, wasting money or time using a bad one. Let's look at the analysis of merge sort. That's a bit of math, but very instructive, because this really shows the power of the divide and conquer method, and allow us to take a problem that was taking us quadratic time with methods like insertion and selection sort, and get it done in n log n time with merge sort. So that's the proposition. Merge sort uses at most n log n compares and 6 n log n array accesses to sort any array of size n. And the way to prove this proposition is to, from examining the code, to write down what's called a recurrence relation. And all that is, it's a mathematical reflection of what's going on in the code. If we're sorting n items, then let C of n denote the number of compares that we need to sort the n items. In order to get that done, we're sorting the left half and the right half. There's notation ceiling of n over 2 and floor of n over 2. That's the n over 2 round up, n over 2 round down. That's the size of the two subarrays. And we're going to call the same routine for that size, so the number of compares you need for that is C of n over 2, ceiling of n over 2 for the left, and C of floor of n over 2 for the right. And then for the merge, we need at least, at most, n compares. If neither one exhausts, we need exactly n compares. And so, and that's true as long as n's bigger than 1. If there's only one thing, we're not doing any compares at all. So this is a mathematical formula that we derive by examining the code, but it completely describes mathematically an upper bound on the number of compares that are going to be needed. And similarly for the number of array accesses, if you count up the number of times you're accessing an array for a merge, it could be at most 6n. So these are mathematical formulas, and there's techniques for solving them, and we won't go into that. This is not a course in discrete mathematics. But what we can do is show how to solve the recurrence when n is a power of 2. And then it turns out that it holds for all n, which we can prove by induction from the recurrence. So if you have this recurrence, which is similar to the ones that we're talking about, it's exactly the same when n is a power of 2. Let's look at this one. If d of n is 2d of n over 2 plus n, with d of 1 equals 0, then d of n equals n log n. And we'll look at 3 proofs of that, just assuming that n is a power of 2. If n is a power of 2, then n over 2 is also a power of 2, so the recurrence makes sense. So this is just a graphical representation. If we want to compute d of n, we want to compute d of n over 2 twice. So that's 2. And then the extra cost for the merge is n. But if we're going to do this twice, then we have 2 n over 2s. Whoops. We have 2 n over 2s. And then for each one of these, we have divided into n over 4s, and each one of those 4 n over 4s has an extra cost for the merge of n over 4. Well, 2 over n over 2 is n, 4 n over 4 is n, and we keep going down and doing that till we get down to d of 2, and we always, for the extra cost of the merge, we have n. And how many stages do we have here? Well, it's the number of times you divide n by 2 to get down to 2. That's exactly log base 2 of n. So the grand total of all the costs for the merge, which is where the compares are, is log n times n, n log n. That's kind of a graphical proof, or a proof by picture, that that recurrence has that solution. Here's a little bit more mathematical one. We write the recurrence down, and then we divide both sides by n. So then it says d of n over n equals d of n over 2 over n over 2 plus 1. So it's dividing by n. So now this is a recurrence that telescopes. The first term on the right-hand side is exactly the same as the left-hand side, so we can apply the same formula. And all it does is divides by 2 again and then throws out another 1. And we keep doing that until we get down to d of 1, which is 0. And when we've done that, we've thrown out log n 1s. So we get d of n over n equals log n, or d of n equals n log n. That's another proof by expansion. Or using either one of those techniques, you could just get the idea that d of n is close to n log n, or you can write a program to expand the recurrence and find that. And then once we have the idea that d of n equals n log n, we can plug back into the original formula. With the inductive hypothesis that d of n equals n log n, we want to show that d of 2n equals 2n log 2n. Using the recurrence, d of 2n equals 2d of n plus throw out the 2n, plugging in n log n, we get the desired result. And you use this same idea on our initial recurrences for compares and array accesses to show that the number of compares and array accesses is proportional to n log n for merge sort. So that's the running time. Merge sort is fast. The other thing that we usually want to know is memory. And one of merge sort's characteristics is that in practical applications, it uses extra space proportional to n. That is, we need that extra auxiliary array for the last merge. We took 2 sorted subarrays and we talked about an abstract in-place merge, but we didn't have an actual in-place merge. We were using an extra subarray. And in-place is important. A lot of times we're sorting everything we have. We want to fill up the memory with stuff to sort and then sort it. Insertion, selection, and shell sort were in place. They don't use much extra memory. But merge sort, you can only sort really half of what you can fit in memory because you need that auxiliary array for the other half. If you want, again, if you think that the things we're studying are easy, think about the idea of actually doing an in-place merge. People have come up with methods for getting this done, so it's theoretically possible, but the methods are generally too complex to be useful in practice, and they're not used. But there could be out there some easy way to do an in-place merge. That's another great algorithm waiting to be discovered. Now, there's a number of practical improvements that we can use to make merge sort even more efficient than the simple one that we've looked at. And we'll take a look at those because they're examples of techniques that we can use for other algorithms. First thing is that merge sort is too complicated to use for tiny arrays. So say the subarrays are only of size 2 or 3 or 4. There's too much overhead with the recursive calls and so forth to get that done efficiently. And what's worse is the recursive nature of the sort definitely means that there's going to be lots of subarrays to be sorted. So one improvement that we can make is to use insertion sort and just cut off and use insertion sort, which is simple and efficient for small subarrays. So that's adding this one line of code to merge sort. We'll make it quite a bit faster, maybe 20% faster. A second improvement that we can make that'll improve the performance for cases when the array is partly sorted is to just stop if it's already sorted. And that's going to happen in the case where the biggest element in the first half is less than or equal to the smallest item in the second half. That means it's done. So that's easy. We just put a test in the recursive merge sort for that to this one line of code to check whether we're done. That way, for example, if you were to call merge sort for an array that's already in order, it would just do this test every time, and it would be done in linear time. That's pretty helpful, although not totally helpful, but there's a lot of situations where that's helpful. The other thing that's possible to do, and it's a little mind-bending, so recommended only for experts, is to save a little bit of time. You don't really have to copy over into the auxiliary array. You can kind of switch the role of the input in the auxiliary array every time you make a recursive call. You still need that array, but you can set up the code in this way, which sorts To sort an array, put the result in the other one. To merge an array, put the result back in the first one. So it's a recursive argument switchery to get the job done. And it's effective. It means you don't have to actually move items. And that saves a little bit of time. So here's a visualization of what the practical merge sort might look like. And this is with a big cutoff to small subfiles. So you get a visual feeling of how this sort gets the job done. It sorts the first little chunk and then the next little chunk and then merges those together and so forth and so on. A good visual representation of how merge sort gets its job done. That's the basic merge sort algorithm that we're going to look at different versions of next. Next, we're going to look at a bottom-up version of merge sort. While merge sort is easy to understand as a recursive program, this bottom-up version that has no recursion is also quite simple to understand and to code up. The basic idea is to think of the array as being a little, at the beginning, a set of little sorted subarrays of size 1. And then what this method will do is go through and merge those little subarrays of size 1 together in pairs to get subarrays of size 2. Then the whole array consists of sorted subarrays of size 2. Then we make another pass through to get size 4 and then size 8 and so forth. So as you can see in this example, we start out by merging the first two subarrays of size 1 to make an array of size 2 EM that's sorted. And then do the same thing for the next two elements and the next two and so forth until eventually, instead of 16 individual elements, we have 8 sorted subarrays of size 2. Then in another pass through, we can take the EM and the GR and merge them together to make EGMR, and the ES and the OR, merge those together to make EORS and so forth, and we have 4 subarrays of size 4. One more pass makes 2 subarrays of size 8, and then the last pass is just a sorted array. The bottom line in this is a sequence of passes through the whole array, and there's no recursion needed at all. It's extremely easy to code up, as you can see from this code. We use the same merge code as before, and we take a nested for loop. The first one is the size of the subarray. And this loop gets executed only log n times because each time we double the size of the subarray until we get to n. And then we pass through picking out from low to low plus size minus 1. And then the next part is low plus size minus 1. Until we run to the end of the array, we might not have a full subarray of size SZ. That is a fully complete industrial strength code for sorting. The only downside, as with regular merge sort, is that it uses extra space proportional to the size of the array. But otherwise, that's a fine method for merging. That's bottom-up merge sort. If you look at this visual trace, you can see how it works. The thing is totally unsorted. Then it gets sorted into subarrays of size 4, then 8, 16, and 32. Now in this case, the second subarray to be sorted is smaller, but the merge routine doesn't really care about that so much. It can merge things that are not equal in size, and then we get a final sorted array. Whatever the size, bottom-up merge sort gets the job done in log n passes, each pass using about n compares for a total cost of about n log n. With merge sort is a good opportunity to take a look at the intrinsic difficulty of the sorting problem. That's called complexity, and we'll look at that next. The idea of complexity is it's a framework for studying the efficiency of all the algorithms for solving a particular problem. That's called computational complexity. And in order to do this sensibly, we need what's called a model of computation, the operations that the algorithms are allowed to perform. For sorting, that's kind of straightforward. What we're going to do is have a cost model where we count the comparisons. Now, in framing the difficulty of problems, we'll need two things. One is what's called an upper bound, which is a cost guarantee that's provided by some algorithm for solving the problem. That's an upper bound on how difficult it is to solve the problem. We have an algorithm that can solve it. It's at least that easy. And then we also look for a lower bound, which is a limit on the cost guarantee of all algorithms. No algorithm can do better. Now what we seek ideally is what's called an optimal algorithm, where we prove that the upper bound and the lower bound are the same. That's an algorithm that we know that has the best possible cost guarantee. That's the ideal for solving any problem. So for sorting, let's look at what each of these are. The model of computation is what's called a decision tree. What that means is that all we can use is compares. That's the only way we can access the data. So our cost model is the number of compares. Merge sort provides an upper bound. That's an algorithm that's guaranteed to get the sort done in time proportional to n log n. And what we'll look at now is the lower bound. There's a trivial lower bound which says you have to look at all the data, that's n. And we'll look at a better lower bound and see that merge sort is optimal. So here's the basic idea for proving a lower bound for sorting. So let's say we have three different items, A, B, and C. Whatever algorithm we have is going to first do a comparison between two of the items. Let's say they're A and B. And then there's two cases. Either it's yes or it's not yes. Let's say they're distinct. And there'll be some code between the compares, but either way, then there's going to be a different compare. If A is less than B, maybe the next compare is B against C. And if you find that B is less than C and A is less than B, then you know that they're in any algorithm that does that knows that the items are in the order A, B, C. If B less than C goes the other way, then it takes another comparison to determine the order. In this case, if C is less than B and A is less than C, then those three compares show that the order has to be A, C, B. And if C is less than A, then it's got to be C, A, B. Those three compares that C is less than A, C is less than B, and A is less than B. The only possibility is C, A, B. And continuing on the right, perhaps the next compare is A less than C, and maybe if C is less than A, another compare B less than C. So in this case, if you go from top to bottom in the tree, with three compares at most, you can determine the ordering of the three different items. The idea of the lower bound generalizes this argument to figure out the number of compares that you need for a minimum to determine the ordering among n items. Now, the height of the tree, as I just mentioned, is the worst case number of compares. Out of all the orderings, the one that's furthest down in the tree, that's the worst case. And so the algorithm, no matter what the input is, the tree tells us a bound on the number of compares taken by the algorithm. And there's got to be at least one leaf for each possible ordering. If there's some ordering that is not appear in a tree corresponding to a particular algorithm, then that algorithm can't sort, can't tell the difference between two different orderings. So the lower bound is a proposition that uses a decision tree like that to prove that any compare-based sorting algorithm has to use at least log base 2 of n factorial compares in the worst case. And by Stirling's approximation, we know that log base 2 of n factorial is proportional to n log base 2n. And then the proof is generalizes what I talked about in the decision tree on the last slide. We assume that the array consists of n distinct values, and there's a decision tree that describes the performance of any algorithm, the compare sequence done by any algorithm to determine the n factorial different orderings. So this tree has to have at least n factorial leaves, and if the tree is of height h, it has at most 2 to the h leaves. The the tree that has the most leaves of height h is totally complete, and that one has 2 to the h leaves. And those observations give us the lower bound. 2 to the h has to be greater than or equal to the number of leaves, and the number of leaves has to be greater than or equal to n factorial, so that implies the height of the tree has to be greater than or equal to log base 2 of n factorial, which is proportional to n log n by Stirling's formula. That's a lower bound on the complexity of sorting. So we knew that the upper bound was proportional to n log n, and we just proved that the lower bound is proportional to n log n, and that means that merge sort is an optimal algorithm. That's the first goal of algorithm design, is to try and find optimal algorithms for the problems that we need to solve. Now, you have to take these results in context. Really, what we proved is that merge sort is optimal with respect to number compares, but we already know that it's not optimal with respect to space usage. Merge sort uses twice as extra space proportional to the size of the array it has to sort. And simple algorithms like insertion sort don't. They don't use any extra space at all. So what we want to take from these theoretical results is a guide when we're looking at implementations and trying to solve practical problems. In this example, what the theory tells us is, don't try to design a sorting algorithm that guarantees to use substantially fewer compares than merge sort. Say half n log n compares. Is there a method that uses half log n compares? The lower bound says no. And that's a very useful thing, because otherwise we might try to define such an algorithm. On the other hand, maybe there is an algorithm that uses n log n compares and also uses optimal space. It's optimal with respect to both space and time, and that's what we're going to look at soon. The other thing is that the lower bound is for the particular model of computation being studied, in this case compares. It might not hold if the algorithm has more information about the keys. For example, if it's known that the input is almost ordered. We saw that insertion sort can be linear time for files that are almost ordered. Or if something about the distribution of key values. If there are a lot of equal keys, we can get it sorted faster than in n log n. And maybe the way the keys are represented, we'll look at different methods that take advantage of such properties. So partially ordered arrays, we may not need n log n compares. Duplicate keys, we may not need n log n compares. We're going to look at a method that gets that done in linear time in a lot of situations. And later on, we'll look at digital properties of keys where we can use digit or character compares instead of whole key compares and get a faster sort for certain practical applications. Computational complexity is a very useful way to help us understand properties of algorithm, help guide our design decisions. Finally, we talk about stability. This is really one of the rules of the game, but it's much easier to talk about in the context of the real algorithms that we've seen so far. And really, it doesn't make sense if you don't know about comparators, which we just introduced. So the typical application that I just used as an example is, say, this set of student records. So we have them sorted by name. This is, say, something that we do just before assigning final grades. Maybe the third line there is the final grade. So it's all fine, it's sorted by name, but then in order to distribute it out to the people leading each of the sections, what we want to do is sort by the second field, sort by section. The problem is that when we do that, it messes up the sort by name. And that's annoying. You might assume that once you have it sorted by name, that when you sort it by the second field, then it should maintain the sort of by name for all that have equal keys in that second field. Actually, not all sorts preserve that property. That's called stability. And clearly, it's worthwhile to think about, for your application, whether you want or need a stable sort. It's an annoying surprise for many people in many applications. So a stable sort is a sort that preserves the relative order of items with equal keys. Which of our sorts are stable? That's an interesting question that we'll take a look at now. The quick bottom line is that insertion sort and merge sort are stable, but not selection sort or shell sort. And even within that bottom line, there's implementations that maybe are not stable. You have to carefully check the code to be sure. Always in this class, we have an exercise or exam question. Is this version of this sort stable or not? So students learn to recognize whether code is stable. So this is just another typical example where we've got things sorted by time. And then what we want to do is maybe these are important events, people buying tickets to a rock concert. And then we want to sort by location. What we'd hope is that it would keep the sort by time, but this is a non-stable sort that doesn't do that. So then out in the locations, they're going to have to resort it if they use one of these. But if they use a stable sort, then it stays sorted by time. Lots of applications you want stability. All right, so let's just look at each of the algorithms that we've considered so far. Insertion sort. Insertion sort is stable. Why is it stable? Well, we never move equal items past one another. In this example here, when we get A1, well, that's, so in this case, the index is just when it appears in the array, it's just A's and B's. When we get our second A, we stop the sort as long as we're not less. We're equal, we're not less, we stop it. So we never move an equal item past another one. If this less were less than or equal, then it wouldn't work. Or if we did it the other way around and it proceeded accordingly. So equal items never move past each other in this code, so therefore insertion sort is stable. But selection sort is not stable. Usually the way to show that a sort is not stable is just to see if it has a long distance exchange that might move an item past some equal item. So in this case, for example, for selection sort, when we do that first exchange, where we found the minimum A and B is in position 0, we did a long distance exchange. And that catapulted that first item past any item that it might be equal, putting them out of order. And that may not get fixed, so that sort is not stable. It might move items past some equal item and leave a result where items that are equal are in different order than they were originally in the file. Selection sort is not stable. Shell sort also has long distance exchanges, so it's not stable. It moves keys past other keys that could be equal. And so it's easy to construct examples showing that selection sort is not stable. And what about merge sort? Merge sort is stable. Well, it's stable as long as the merge operation is stable. And that operation is going to be stable depending on how we code it. And in our code, if the two keys are equal, it takes from the left subarray. So that means that it'll always take the, if there's two sets of equal keys, it'll preserve the relative order. And that's enough to show that the merge operation is stable, and then therefore merge sort is stable. Stability is an important property in sorting algorithms. Merge sort is not only efficient, it's also stable.